What if the moon has been keeping the same face toward us for more than 4.5 billion years? Not by accident, but by mathematical inevitability. It rotates once every 27.3 days, exactly the same time it takes to orbit Earth. That precision is called tidal locking. It sounds poetic, but it's physics. Early in its history, when the moon spun much faster, Earth's gravity stretched it, slowed it, reshaped it until rotation and orbit became one synchronized motion. Tonight, on Velorin Sleepy Space Mysteries, we'll gently explore how gravity, friction, angular momentum, and billions of years of time turned chaos into perfect balance. This is not myth. It is measurable. If calm scientific journeys like this help you relax, subscribe, like, turn on the notification bell, and consider joining our membership to support deeper explorations. And before we continue, tell me in the comments where you're listening from. Let's see how far this quiet signal travels across Earth. Now, let's begin. 4.5 billion years ago, the moon was not calm. It had just formed from the debris of a catastrophic collision between the young Earth and a Mars-sized world often called Theia. In those early days, the moon orbited far closer to Earth than it does now, perhaps only a few tens of thousands of kilometers away. It glowed with leftover heat from its violent birth, its surface partly molten, its interior restless, and it spun quickly. One full rotation may have taken less than 10 hours. This was not yet the quiet silver companion we know today. It was a hot, rapidly rotating world, circling close, moving fast, full of energy. To understand what happened next, we turn to a simple equation written more than 3 centuries ago by Isaac Newton. It is usually written as F equals G times M1 times M2, divided by R squared. Said slowly, it means this: the force between two objects equals a constant of nature, multiplied by the mass of the first object, multiplied by the mass of the second object, and then divided by the distance between them multiplied by itself. In other words, divided by the square of the distance. The letter F stands for force. The letter G is the gravitational constant, a small number that sets the strength of gravity everywhere in the universe. The two M's represent the masses of the two bodies, in this case Earth and Moon, and R is the distance between their centers. This equation tells us something both simple and profound. Every mass attracts every other mass. The larger the masses, the stronger the attraction. And the closer they are, the dramatically stronger that attraction becomes, because distance is squared in the denominator. If you cut the distance in half, the force does not merely double. It becomes 4 times stronger. In the early solar system, when the moon was much closer to Earth than it is today, the gravitational pull between them was not just a little stronger. It was many times stronger. But gravity does more than pull objects straight toward one another. When two bodies are close, gravity does not act evenly across their entire shapes. The side of the moon facing Earth feels a slightly stronger pull than the far side. This difference is small in absolute terms, but over planetary scales it matters. It creates stretching. It creates tidal forces. The moon, still warm and not yet fully rigid, would have been gently elongated along the line pointing toward Earth, forming what we call tidal bulges. Imagine the young moon spinning quickly while these bulges try to align with Earth's pull. If the moon rotates faster than it orbits, those bulges do not point exactly at Earth. They are dragged slightly ahead by the moon's rotation. Earth's gravity then pulls back on those misaligned bulges. That pull creates a torque, a twisting force, and that twisting force acts like a brake. Over immense spans of time, it slows the moon's rotation. Energy is not destroyed in this process. The rotational energy of the moon is gradually converted into heat through internal friction. At the same time, angular momentum is exchanged between Earth and Moon. The system adjusts. The moon's spin slows. Its day grows longer. What may once have been a 10-hour rotation stretches into dozens of hours, then hundreds, then thousands. This slowing continues until a remarkable balance is reached. The moon eventually rotates once on its axis in exactly the same amount of time it takes to orbit Earth. Today, that shared period is about 27.3 days. One spin, one orbit, perfect synchronization. When that equality is reached, the tidal bulges no longer move ahead or lag behind. They point almost directly toward Earth. The torque fades. The braking largely stops. A stable configuration emerges. So from chaos and heat, from rapid spinning and immense gravitational strain, a quiet pattern forms. The same face of the moon turns toward Earth again and again. What began as violent motion becomes steady rhythm. All of it guided by that simple relationship. Force equals the gravitational constant times mass 1 times mass 2, divided by distance squared. Gravity pulled, gravity stretched, gravity slowed, and over billions of years, gravity sculpted the calm, familiar moon we see tonight. Because the side of the moon facing Earth is slightly closer than the far side, Earth's gravitational pull is not equal across the lunar body. This difference is called a gravitational differential force. The result is distortion. The moon developed tidal bulges, one facing Earth, one on the opposite side. If the moon had not been rotating, those bulges would have aligned perfectly along the Earth-Moon line. But the moon was spinning rapidly. The rock beneath those bulges tried to move forward while Earth's gravity tried to pull them back into alignment. This misalignment is the key. When the bulges are dragged slightly ahead of the Earth-Moon axis, gravity pulls backward on them. That backward pull creates torque, a twisting force. Torque changes rotational motion. It acts like a brake. Inside the moon, rock is not perfectly rigid. As the body deforms and relaxes during each rotation, internal friction converts mechanical energy into heat. This process is tidal friction. It does not stop motion instantly. It drains it slowly, very slowly. The moon's rapid 10-hour spin lengthened. Hours became days. Days became weeks. Energy was not destroyed. It was redistributed. Angular momentum must be conserved in a closed system. As the moon lost rotational energy, that angular momentum was transferred into its orbit. The moon began drifting outward. Even today, that outward drift continues at about 3.8 centimeters per year, a rate confirmed by laser reflectors left on the surface during the Apollo missions. Those reflectors allow precise measurements of distance by timing how long light takes to return. The Earth-Moon system is still evolving. While the Moon's spin slowed, its orbital period remained governed by gravity. Today, the Moon orbits Earth once every 27.3 days. Its average orbital speed is about 1 kilometer per second. That motion has not stopped. What changed was the relationship between rotation and orbit. Synchronous rotation occurs when angular velocity of spin equals angular velocity of orbit. In simple terms, one rotation per orbit. Mathematically, if omega_spin equals omega_orbit, the same hemisphere always faces the primary body. When the Moon's rotational period lengthened to match its 27.3-day orbital period, torque from tidal friction diminished dramatically. The bulges no longer lagged significantly. The braking process effectively completed. The Moon became tidally locked. From Earth, we see one face. But the system did not freeze. It reached a minimum energy configuration. Earth itself participates in this exchange. The Moon raises tides in Earth's oceans. Those moving waters dissipate about 3.7 terawatts of energy globally through friction with coastlines and the seafloor. That energy loss slows Earth's rotation by roughly 1.7 milliseconds per century. As Earth's spin slows, angular momentum continues transferring to the Moon's orbit. The process is reciprocal. Gravity is not dramatic. It is patient. Over billions of years, it sculpts motion toward equilibrium. Evidence of this ancient sculpting is written into the Moon's structure. The Grail mission mapped the Moon's gravitational field in exquisite detail. It revealed mass concentrations, mascons, beneath large impact basins. These density variations slightly affect the Moon's rotation and orbit. They are geological fingerprints of tidal evolution. The Moon's crust is not uniform. The far side is on average about 15 kilometers thicker than the near side. Early tidal heating and asymmetrical cooling likely contributed to this imbalance. The side facing Earth remained warmer longer. Lava flooded the thinner crust, forming the dark Maria we see today. The far side remained thicker, more heavily cratered, less volcanic. Tidal locking shaped geology. Even now, the lock is not perfectly rigid. Because the Moon's orbit is slightly elliptical and its axis slightly tilted, we observe libration, a gentle oscillation. Over time, we can see about 59% of the lunar surface, not just 50%. The Moon appears to rock subtly east-west and north-south. These oscillations arise from orbital eccentricity, axial tilt, and viewing geometry from Earth's rotating surface. Stillness is an illusion created by slow timescales. The Moon continues to move at 1 kilometer per second through space, continues drifting outward. Earth continues slowing. Angular momentum continues flowing through the system like a quiet current. What ended billions of years ago was not motion. It was imbalance. The early Moon, spinning in under 10 hours, contained excess rotational energy. Tidal friction dissipated that excess as heat. Torque reduced the mismatch between spin and orbit. The system sought the lowest possible energy configuration while preserving total angular momentum. That configuration is what we see today. one face toward Earth, one orbit every 27.3 days, one rotation every 27.3 days. Gravity achieved harmony through loss. If the moon had been smaller, tidal braking would have been weaker. If it had been farther away initially, synchronization might have taken much longer. But given enough time and sufficient gravitational coupling, tidal locking is not unusual. Many moons in the solar system share this fate. What makes ours remarkable is the precision and the scale. From violent beginnings to mechanical inevitability. From molten chaos to geometric balance. And yet, this is not the end of the story. The synchronization we observe is not static. The moon continues to recede. Earth's day continues to lengthen. In the distant future, billions of years from now, Earth itself will become tidally locked to the moon. Both bodies will face each other permanently, rotating in mutual synchrony. Dynamic equilibrium is not frozen. It is balance maintained through constant adjustment. Every tide on Earth, every millimeter measured by lunar laser ranging, every subtle libration is evidence that the system is alive with motion, just extremely slow motion. Gravity does not hurry, finishes. If you are still listening to this slow mechanical story of torque, friction, angular momentum, and 4.5 billion years of patient reshaping, type 1 in the comments. The moon may look still, but what you are seeing is gravity's slow engine at rest. Not because it stopped working, but because it completed its work. When the moon finally reached synchronous rotation, something extraordinary happened, but it did not happen in a single moment. There was no audible click, no sudden halt. The braking force simply diminished as the misalignment between the tidal bulges and Earth's gravitational pull approached zero. The torque that had been draining rotational energy for hundreds of millions of years faded because the geometry no longer demanded correction. The bulges aligned almost perfectly with Earth. The internal friction dropped. The cosmic brake released. From that point forward, one lunar hemisphere would always face Earth, not because motion ended, but because motion became perfectly matched. To understand the elegance of this, consider angular velocity more precisely. Angular velocity is simply the speed at which something rotates. It tells us how quickly an object turns around its axis, and it is usually measured in radians per second, which is just a precise way scientists describe rotation. For the moon today, something remarkable is true. The speed at which it spins on its own axis is exactly the same as the speed at which it travels around Earth. In mathematical language, scientists write this as omega spin equals omega orbit. Said out loud, that means the moon's spin rate is equal to its orbital rate. Because the moon takes about 27.3 days to complete one full trip around Earth, it must also take 27.3 days to complete one full rotation on its axis. One orbit, one rotation, the same length of time. That perfect equality is why the same side of the moon always faces us. Any deviation from that equality produces restoring torque. If the moon tried to rotate slightly faster, the tidal bulge would shift ahead of Earth and gravitational torque would slow it back down. If it rotated slightly slower, the bulge would lag and torque would speed it up. The system self-corrects. This is why tidal locking, once achieved, is stable. It is not fragile. It is energetically favored. But the energy exchange that led to this stability left physical evidence. In the moon's early history, tidal heating likely generated substantial internal heat. Though not as extreme as Jupiter's moon Io today, the young moon experienced enough internal flexing to influence magma movement beneath its crust. Basaltic lava later flooded large impact basins on the near side between 3 and 3.5 billion years ago, forming the dark Maria visible even to the naked eye. The far side, with its thicker crust, did not experience the same degree of volcanic resurfacing. The crustal thickness difference, roughly 15 kilometers thicker on the far side, remains one of the clearest structural asymmetries in the lunar body. Data from NASA's Grail mission revealed how mass concentrations beneath these basins slightly alter the moon's gravitational field. These mascons create subtle variations in orbital motion, which must be accounted for when navigating spacecraft. They are remnants of ancient impacts and lava flows, but they also reflect how tidal forces once redistributed internal mass. The moon's shape itself is slightly elongated along the Earth-Moon axis, a frozen memory of tidal deformation from when it was closer and softer. Even though the moon appears rigid today, its structure remembers the era when it was more easily stretched. Meanwhile, the Earth did not remain unchanged during this exchange. As tidal friction acted within Earth's oceans, rotational energy was continuously dissipated as heat. Approximately 3.7 terawatts of power are currently lost through tidal interactions, mostly through oceanic turbulence and friction against continental shelves. That may sound abstract, but it is comparable to a significant fraction of global human energy consumption. Every high tide and low tide represents a tiny transaction in this angular momentum economy. Because Earth rotates faster than the moon orbits, tidal bulges on Earth are slightly ahead of the moon's position. This forward offset pulls the moon ahead in its orbit, giving it additional orbital energy. That added energy pushes the moon outward at about 3.8 centimeters per year, a rate measured directly using laser ranging experiments targeting reflectors left by Apollo astronauts. These measurements are precise to the millimeter. Over millions of years, small distances accumulate. Hundreds of millions of years ago, the moon was significantly closer. Geological records from tidal sediments suggest that Earth's day was once much shorter, perhaps around 21 or 22 hours. The lengthening continues at about 1.7 milliseconds per century. This may seem negligible, but over deep time it becomes transformative. Tidal locking, then, was not a one-sided event. It was a mutual evolution. The moon lost spin and gained distance. Earth lost spin and lengthened its day. Angular momentum moved outward through the system while total angular momentum remained conserved. This is the quiet discipline of physics. Nothing is lost, only rearranged. The current state of synchronous rotation represents a minimum energy configuration for the moon's rotation given its orbital distance. But because Earth continues to slow, the system has not reached its ultimate equilibrium. In the distant future, billions of years from now, Earth's rotation will slow enough that its day equals the moon's orbital period. At that point, both bodies will be tidally locked to each other. The moon will hover permanently above one hemisphere of Earth. The tides will diminish dramatically. Motion will not cease, but it will become symmetrical. For now, however, we live in the intermediate stage. The moon is locked, Earth is not. The outward drift continues. The energy exchange continues. The synchronization is stable but not static. It is a dynamic equilibrium maintained by constant microscopic adjustments. Even libration, the subtle rocking motion that lets us see 59% of the lunar surface, reminds us that perfection in celestial mechanics includes small oscillations. The moon nods and sways slightly because its orbit is elliptical and its axis tilted. These tiny motions are allowed within the broader locked state. They do not break the synchronization. They are part of it. Gravity's slow engine is still running, though its work is mostly complete on the lunar side. What appears frozen is simply balanced. What appears eternal is the outcome of billions of years of energy redistribution. The moon does not resist Earth. It does not cling. It has settled into the configuration that wastes the least energy. That is the deeper truth of tidal locking. It is not a coincidence, not a miracle, not an accident of alignment. It is the inevitable result of gravity acting over time on a rotating, deformable body. And time, in celestial mechanics, is always sufficient. To fully appreciate how inevitable this outcome was, it helps to imagine the early Earth-Moon system as a continuously adjusting machine governed by conservation laws. After the Theia impact, Earth itself was rotating far faster than it does today. A day may have lasted only 5 or 6 hours. That rapid spin stored enormous rotational kinetic energy. The newborn moon, orbiting much closer than its current average distance of 384,400 kilometers, moved quickly through a much stronger gravitational field. The interaction between two rapidly rotating, partially molten bodies created a powerful exchange channel for angular momentum. Tidal forces were not gentle in those first tens of millions of years. They were immense. The tidal bulges raised on the moon were proportionally much larger in those early days, because the difference in gravity between the near side and the far side was stronger when the moon was closer to Earth. When two objects are close together, gravity does not just pull harder overall, it also changes more sharply from one side to the other. That sharper change creates stronger stretching. Remember that gravitational force follows a simple rule. It is proportional to 1 divided by distance squared. Said more gently, gravity becomes stronger as distance becomes smaller, and it does not increase in a simple one-to-one way. If you reduce the distance even a little, the force grows much more than you might expect. Cut the distance in half and the force becomes 4 times stronger. So when the young moon orbited much nearer to Earth, the gravitational pull was dramatically more intense, and the tidal bulges were correspondingly larger. That means the differential pull between the near side and far side of the moon was far stronger in the past. Larger deformation means more internal flexing. More flexing means more friction. More friction means faster dissipation of rotational energy. This is why tidal locking of the moon likely occurred relatively early in its history, within perhaps a few 100 million years. The system was energetically active enough to complete the synchronization efficiently. Inside the moon, this flexing produced heat. Though much of that heat has long since escaped into space, models suggest that tidal heating contributed to maintaining partial melt in the lunar mantle during its early evolution. This heating may have influenced the formation of the lunar magma ocean and the later crystallization sequence that determined crustal thickness. The asymmetry we see today, where the far side crust averages about 15 kilometers thicker than the near side, may be partially rooted in how energy was distributed during that era of intense tidal interaction. The side facing Earth experienced prolonged thermal influence, while the far side cooled differently. This structural imbalance became frozen into the moon's geology as the system settled into synchronous rotation. Once the rotational period approached the orbital period of 27.3 days, the braking torque decreased sharply. The mathematics of torque in tidal systems shows that torque is proportional to the sine of the angle between the tidal bulge and the line connecting centers of mass. As that angle shrinks toward zero, torque diminishes. When alignment becomes nearly perfect, energy dissipation drops dramatically. That is why tidal locking tends to snap into a stable equilibrium once synchronization is nearly achieved. It is not that the forces vanish. It is that the geometry no longer produces significant misalignment. The moon now rotates at precisely the rate required to keep its longest axis roughly aligned with Earth. Yet the word precisely must be understood in physical terms, not poetic ones. The moon's orbit is slightly elliptical. The speed varies along that ellipse according to Kepler's laws. When it is closer to Earth, it moves slightly faster. When farther, slightly slower. Because its rotation rate is nearly constant, this variation produces longitudinal libration, allowing observers on Earth to glimpse a little beyond the average limb. Similarly, its axis is tilted by about 6.7 degrees relative to its orbital plane, producing latitudinal libration. These oscillations mean the lock is not a rigid clamp. It is a balanced oscillatory system. Over time, these small deviations are corrected by gravitational restoring torques. The moon wobbles within narrow bounds, never straying far from alignment. Meanwhile, Earth continues to pay the energetic cost. Tidal friction in Earth's oceans dissipates approximately 3.7 terawatts of power. That energy comes directly from Earth's rotational kinetic energy. As Earth slows by roughly 1.7 milliseconds per century, the lost angular momentum flows into the moon's orbital motion, increasing its semi-major axis at about 3.8 centimeters per year. Laser ranging experiments using reflectors left during the Apollo missions confirmed this recession with extraordinary precision. Over 1 million years, that small annual drift amounts to 38 kilometers. Over 100 million years, it amounts to 3,800 kilometers. Geological records of ancient tidal cycles preserved in sedimentary rock confirm that days were shorter hundreds of millions of years ago. The evidence aligns with modern measurements, reinforcing that this is not theory alone but an observable, ongoing phenomenon. The Earth-Moon system is therefore not static but evolving toward a deeper equilibrium. Present, only the moon is tidally locked. Earth rotates faster than the moon orbits. But in the far future, if given enough time and absent interference from solar evolution, Earth's rotation would slow until one day equals one lunar month. At that point, the system would reach mutual tidal locking. Both bodies would show the same face to each other. The transfer of angular momentum would cease because no misalignment would remain to generate torque. Energy exchange would approach zero. This configuration represents the minimum energy state for a two-body gravitationally bound rotating system. It is not an accident of history, but a predictable endpoint under Newtonian mechanics. The moon's stillness, then, is not a singular event but a stage in a long gravitational negotiation. Gravity does not rush toward equilibrium. It inches toward it, centimeter by centimeter, millisecond by millisecond, terawatt by terawatt. The moon achieved its lock because time allowed torque and friction to do their quiet work. And even now, that work continues, though at a slower pace, guiding both worlds toward a symmetry billions of years in the making. There is another layer to this story that makes tidal locking feel less like an isolated curiosity and more like a universal rule. If you place any rotating, deformable satellite in orbit around a much larger body and wait long enough, gravity will attempt the same sculpting. The timescale depends on distance, size, rigidity, and internal structure, but the direction of evolution is predictable. Energy dissipates, misalignment shrinks, rotation synchronizes. In the case of the moon, the combination of its relatively large size compared to Earth and its early proximity accelerated this process. The twisting force, or torque, acting on a tidally distorted body can be roughly described in a simple way. It is proportional to the radius of the satellite raised to the fifth power, divided by the orbital distance raised to the sixth power. Said more gently, you take the size of the moon or satellite and multiply it by itself 5 times. Then you take the distance between the two bodies and multiply that distance by itself 6 times. The torque scales with the first number and shrinks with the second. What matters most is how steeply this depends on distance. Because the distance is raised to the 6th power, even a small change in separation makes a dramatic difference. If the distance is reduced slightly, the torque does not just increase a little. It increases enormously. That is why, in the early days when the moon orbited much closer to Earth, tidal forces and the resulting twisting effect were vastly stronger than they are today. Early closeness was not a minor detail. It shaped everything. When the moon orbited much nearer to Earth, tidal torque was many times stronger than it is today. That is why the breaking phase likely occurred early rather than gradually over the entire 4.5 billion years. Once the moon reached its 27.3-day synchronous state, the character of the interaction shifted. The major rotational energy loss had already occurred. What remained was the continued transfer of angular momentum from Earth's faster spin into the moon's orbit. This is the phase we are still living through. The moon's average orbital speed today is about 1 kilometer per second, and that speed very slowly decreases as its orbital radius increases. According to Kepler's third law, as the semi-major axis grows, orbital period lengthens. So in the deep past, when the moon was closer, its orbital period was shorter. That means once the moon first became tidally locked, a lunar month was shorter than 27.3 days. The lock always matches rotation to orbit, but the duration of both changes as distance evolves. This is an important subtlety. Tidal locking fixes equality, not duration. Duration depends on orbital distance, which continues to change. Earth's slowing rotation is equally measurable. A reduction of 1.7 milliseconds per century may seem trivial, but over 100 million years that accumulates to roughly 28 minutes. Fossil coral growth rings and tidal rhythmites preserved in ancient sedimentary rocks indicate that hundreds of millions of years ago, Earth experienced more days per year because each day was shorter. Those geological records align with modern laser ranging measurements, forming a consistent picture across independent lines of evidence. The Earth-Moon system behaves exactly as angular momentum conservation predicts. Total angular momentum remains constant while rotational and orbital components redistribute. The energy dissipated through tidal friction, roughly 3.7 terawatts today, is transformed primarily into heat in Earth's oceans and crust. That heat does not power dramatic geological upheaval. It disperses quietly, a global whisper of friction across coastlines and seabeds. Yet without that steady dissipation, the Moon would not be drifting outward, and Earth would not be slowing. The patient sculptor continues working. The Moon's internal response to this history is still detectable. Data from the Grail mission revealed subtle variations in gravitational acceleration across the lunar surface caused by mascons, dense regions beneath impact basins. These mascons slightly influence the Moon's rotation and orientation. Their distribution also reflects how the lunar crust and mantle responded to ancient tidal heating and volcanic flooding. The far side's thicker crust, averaging about 15 kilometers thicker than the near side, limited large-scale basaltic eruptions there, while the near side's thinner crust allowed vast maria to form between 3 and 3.5 billion years ago. Tidal forces did not create the impacts that formed those basins, but they influenced how the Moon's interior redistributed heat and mass afterward. Even libration, the gentle oscillation that lets us see 59% of the lunar surface over time, fits naturally within this framework. Because the Moon's orbit is slightly elliptical, its orbital angular velocity varies. Its rotational angular velocity remains nearly constant over short timescales. That mismatch produces longitudinal libration. Axial tilt produces latitudinal libration. From Earth's rotating surface, we also gain a small additional perspective shift known as diurnal libration. These effects do not contradict tidal locking. They are refinements within it. They show that the locked state tolerates small oscillations while maintaining overall alignment. The Moon is not welded in place. It is dynamically stabilized. If some disturbance slightly altered its rotation rate, gravitational torque would restore synchronization. That restoring behavior is why synchronous rotation, once achieved, persists over geological time. What makes this entire sequence feel almost serene is its inevitability. There was no decision point, no single dramatic moment when the Moon somehow chose to stop turning relative to Earth. Nothing conscious happened, nothing sudden. The outcome was built into the laws of physics from the beginning. Take Newton's equation, usually written as F equals G times m1 times m2, divided by r squared. In plain language, it says this: The force between two objects depends on how massive they are, and it grows much stronger when the distance between them becomes smaller, because that distance is squared in the denominator. Combine that simple rule with a very real fact about the moon, that rock is not perfectly rigid, that it can flex, stretch, and generate internal friction, and the result becomes unavoidable. As Earth's gravity pulled unevenly on the young, softer moon, it created tidal bulges. As the moon spun, those bulges were dragged slightly out of alignment. Gravity pulled back on them, creating a steady braking effect. Over immense spans of time, that braking converted rotational energy into heat. The spin slowed, not by choice, but by necessity. Physics guaranteed that the excess rotational energy would gradually dissipate, until rotation and orbit matched in quiet synchronization. Torque would act whenever bulges were misaligned. Angular momentum would redistribute until misalignment vanished. The timescale may have spanned tens or hundreds of millions of years, but the direction was fixed from the beginning. Gravity is not creative in its goals. It is relentless in its methods. The moon's synchronous rotation is simply what happens when a rotating satellite is given enough time in the presence of a stronger neighbor. And yet, the stillness we perceive is only partial. The moon continues orbiting at about 1 kilometer per second. It continues receding at 3.8 centimeters per year. Earth continues slowing. The system continues evolving toward a deeper equilibrium that will not be reached for billions of years. What looks like a frozen configuration is actually a balanced exchange still unfolding, just at a pace far slower than human lifetimes can easily perceive. If you are still following this quiet mechanical unfolding of gravity's slow engine, we are approaching the final layer of this part. What this equilibrium means not only for the moon, but for Earth's long-term stability and the geometry of our future sky. If we step back and look at the Earth-Moon system as a whole, what we see is not a frozen sculpture but a continuously adjusting mechanism governed by conservation laws. The moon's tidal locking was not the end of motion. It was the end of excess motion. It marked the point at which rotational kinetic energy had been reduced to the minimum required for stability at that orbital distance. The early moon spun in under 10 hours. Today it rotates once every 27.3 days. That dramatic slowdown represents an enormous transfer of energy. Rotational kinetic energy depends on angular velocity squared. Reducing spin by such a large factor required dissipating vast amounts of energy through internal friction over hundreds of millions of years. That energy did not disappear. Some became heat inside the moon, influencing crust formation and volcanic history. Some was transferred outward as angular momentum, increasing orbital radius. The process was mechanical, not symbolic. Gravity stretched, friction resisted, torque corrected. Time completed the sequence. Now consider the system today. The moon is in synchronous rotation, meaning its angular velocity of spin equals its angular velocity of orbit. The equality omega_spin equals omega_orbit defines the lock. But because the moon's orbit is not perfectly circular and because gravitational influences from the sun introduce small perturbations, the lock operates within a narrow band of oscillation. Libration allows us to see 59% of the lunar surface over time. That number alone reveals something important. Even perfect synchronization permits subtle movement. The moon rocks slightly because its orbit speeds up and slows down along its ellipse. Its rotational rate remains nearly uniform, creating small viewing variations. These are not failures of locking. They are refinements within it. Meanwhile, Earth continues evolving. Tidal friction in Earth's oceans dissipates roughly 3.7 terawatts of energy. That continuous dissipation slows Earth's rotation by about 1.7 milliseconds per century. The effect is tiny on human timescales but decisive on geological ones. Laser reflectors left during the Apollo missions confirm that the moon recedes at approximately 3.8 centimeters per year. Over 1 million years, that is 38 kilometers. Over 100 million years, 3,800 kilometers. The outward drift lengthens the moon's orbital period. Because synchronous rotation ties spin to orbit, the moon's rotational period lengthens as well. The lock persists, but the duration of both rotation and revolution slowly increases. This reveals a crucial point. Tidal locking does not freeze time. It links motions. As distance changes, the shared period changes. The equilibrium is dynamic. It adjusts continuously to the evolving geometry of the system. Angular momentum conservation governs the entire exchange. The total angular momentum of Earth's spin plus the moon's orbital motion remains effectively constant. As Earth loses rotational angular momentum, the moon gains orbital angular momentum. The redistribution is gradual but relentless. There is no external referee enforcing this balance. It arises automatically from Newton's laws and the physical reality of deformable bodies under gravitational stress. In the far future, if the sun's evolution did not intervene, Earth's rotation would continue slowing until 1 Earth day equals 1 lunar month. At that point, Earth would also become tidally locked to the moon. Both bodies would rotate once per orbit, always showing the same face to each other. Tidal torques would vanish because no misalignment would remain to generate them. Energy exchange would approach zero. This configuration represents the minimum energy state for a gravitationally bound rotating pair. It is the logical conclusion of the same process that locked the moon billions of years ago. But we do not live in that final state. We live in the middle of the story. The moon's synchronization feels eternal because 4.5 billion years exceeds our intuitive grasp. Yet, from a mechanical perspective, it is a transitional phase in a long sequence of energy redistribution. The Earth-Moon system has not stopped changing. It has simply slowed to a pace that feels still. Gravity has acted as a patient sculptor, not by carving quickly, but by shaving away imbalance millimeter by millimeter, millisecond by millisecond. The early chaos of rapid spin and strong tidal deformation gave way to alignment. Alignment gave way to stability. Stability now gives way to slow outward drift and rotational deceleration. Nothing in this system is static. Even the moon's apparent stillness is sustained by continuous microscopic corrections. If its rotation deviated slightly, restoring torque would nudge it back into synchrony. If its orbit shifted slightly, gravitational coupling would respond. The balance is maintained not through rigidity but through feedback. That is the deeper meaning of tidal locking. It is not a frozen state but a self-maintaining equilibrium. The moon does not face Earth because it stopped moving. It faces Earth because movement and gravity reached agreement. The agreement is precise, measurable, and ongoing. Every tide on Earth, every millimeter of lunar recession measured by laser ranging, every subtle libration recorded by spacecraft is evidence that the system remains alive with motion. The synchronization achieved billions of years ago is stable, but it is not final. It is part of a continuing evolution governed by conservation laws that do not sleep. So when we look up and see the same familiar lunar face night after night, we are not witnessing stillness in the absolute sense. We are witnessing the outcome of gravity's slow engine, an engine that has already completed its most dramatic work on the moon, yet continues refining the balance between two worlds. If you are still listening to this quiet unfolding of torque, angular momentum, friction, and 4.5 billion years of patient adjustment, type 1 in the comments. What looks motionless in the sky is, in truth, equilibrium maintained in motion. Imagine if the moon were not tidally locked. Imagine it spinning independently, showing us a different face every night. Earth would see shifting patterns of light and shadow, but the deeper difference would be dynamic instability. The gravitational torque between the two bodies would not be in this long-settled minimum energy state. Over geological time, Earth's axial orientation might wander far more dramatically. Instead, we have constancy. The Maria on the near side, those basaltic plains formed billions of years ago, remain visible because nothing erases them. The moon has no weather, no flowing water, no plate tectonics to recycle crust. Craters formed 3 or 4 billion years ago remain almost untouched. The far side, even more so, is a museum of impacts. Stillness preserves history. Each crater rim, each frozen lava flow, is a timestamp from the early solar system. On Earth, erosion would blur such records within millions of years. On the moon, they endure for billions. The very fact that the moon is tidally locked, that one side consistently faced Earth while the other faced deep space, contributed to how that record formed and how it survived. When we look up and see the same face night after night, we are not witnessing repetition. We are witnessing memory. A gravitational decision made billions of years ago, still holding. The near side is the familiar storyteller, marked by dark seas and smooth plains. The far side is the archivist, dense with craters, colder, thicker, more ancient in appearance. Together, they form a complete geological narrative shaped by orbital mechanics. Tidal locking did not freeze the moon in time. It arranged time across its surface. And in that arrangement, gravity created contrast, light and dark, smooth and rugged, visible and hidden. Two hemispheres divided not by choice, but by mathematics. If you were still awake, still traveling across these quiet craters and ancient lava plains, type 2 in the comments. Tidal locking also created something subtler than craters and lava plains. It created orientation. Because one hemisphere always faces Earth, every impact, every thermal cycle, Every gravitational flexing event occurred within a persistent geometric relationship. Over billions of years, that consistency allowed patterns to accumulate rather than randomize. The near side was not just warmer in its early history, it was gravitationally biased. Earth's pull slightly distorted the lunar interior, focusing tidal stresses along predictable directions. When the moon's mantle was still partially molten, those stresses may have helped channel magma upward, preferentially beneath the hemisphere facing us. That is one reason the Great Basaltic Maria clusters so heavily on the near side, particularly in basins like Imbrium and Tranquillitatis, whose lava flows solidified roughly 3 to 3.5 billion years ago. The far side, shielded from Earth's radiant heating and shaped by thicker crust, remained largely resistant to such flooding. Over time, that divergence hardened into two distinct geological personalities on a single world. The average distance of 384,400 kilometers between Earth and Moon may sound vast, but gravitationally it is intimate. At that separation, Earth's tidal force is strong enough to deform solid rock by measurable amounts. Even today, laser ranging experiments show tiny oscillations in the Moon's orientation as it librates, revealing that the interior is not perfectly rigid. Beneath the crust, the lunar core, about 530 kilometers in radius and partially molten, responds subtly to gravitational torque. This internal structure matters because tidal locking is not merely surface alignment. It is a whole-body phenomenon. The Moon's mass distribution adjusted over time until the lowest energy configuration aligned its longest axis toward Earth. That alignment reinforces itself. If the Moon were nudged slightly out of position, Earth's gravity would generate a restoring torque, gently pulling it back. Stability is not passive. It is maintained through constant, tiny corrections governed by physics. The consequences for Earth have been profound. Our planet's axial tilt of approximately 23.5 degrees is stabilized by the Moon's gravitational presence. Without that stabilizing torque, numerical simulations indicate Earth's tilt could vary chaotically between about 10 and 45 degrees over millions of years. Such swings would transform climate regimes. At higher tilts, polar regions would receive far more direct sunlight during parts of the year, potentially melting ice caps entirely before plunging back into deep freezes. At lower tilts, seasonal contrast would weaken, altering atmospheric circulation patterns. The Moon acts as a dampener, limiting the amplitude of Earth's axial precession. In effect, tidal locking created not only a permanent near side and far side, but also a stable climate window in which life could evolve. It is difficult to separate geological stillness from biological consequence. Consider also how impact history differs between hemispheres. Because the far side faces away from Earth, it lacks even the minimal shielding Earth provides against some incoming debris. Earth's gravitational cross-section sweeps up a fraction of potential impactors that might otherwise strike the near side. Over billions of years, that small statistical difference contributes to asymmetry. The far side accumulated more preserved craters, while the near side experienced partial resurfacing through volcanism. The South Pole Aitken Basin, spanning roughly 2,500 kilometers and plunging up to 8 kilometers deep, is not merely large. It is a window into the Moon's deep interior. Data from orbiters suggest material excavated there may originate from the mantle itself. The landing of Chang'e 4 within von Karman crater allowed in situ analysis of minerals such as olivine and low-calcium pyroxene, offering direct clues about mantle composition. None of that exploration would be possible without relay communication positioned near the Earth, Moon L2 point, a gravitational balance location where spacecraft can maintain line of sight with both Earth and the far side. Technology had to adapt to tidal geometry. Even temperature extremes reflect locking. During the long lunar night, far side temperatures can plunge below -230 degrees Celsius. With no atmosphere to redistribute heat, each hemisphere endures prolonged thermal cycles defined by the 27.3-day rotation orbit period. Yet the far side experiences deeper isolation, untouched by Earth's reflected light or radio emissions. That makes it one of the quietest radio environments in the inner solar system, a potential site for future radio telescopes seeking faint cosmological signals from the early universe. In this way, tidal locking has preserved not just ancient craters but also scientific opportunity. Stillness becomes archive. The Maria remain as basaltic records of interior heat. The highlands remain as impact chronicles. The asymmetry in crust thickness, about 15 kilometers thicker on the far side, remains as evidence of early thermal imbalance. Even the Moon's partially molten core remains as testimony to a past shaped by gravitational friction. When we observe the same face each night, we are not seeing repetition. We are seeing conservation. Energy dissipated, motion redistributed, equilibrium achieved. If the Moon were not tidally locked, if it rotated independently, Earth would see alternating hemispheres, but the deeper equilibrium between spin and orbit would not be in this minimum energy state. Over immense timescales, gravity would simply drive it back towards synchronization again. Locking is the natural endpoint of tidal evolution. And because that endpoint was reached early in lunar history, the surface froze in orientation, preserving billions of years of geological memory. Stillness, in this sense, is not stagnation. It is the long-term consequence of energy-seeking balance. If you are still awake, still tracing craters across the hidden hemisphere, and feeling the quiet precision of this gravitational arrangement, type 2 in the comments and continue the journey. There is something quietly profound about the fact that the Moon's stillness has acted as a vault. Because one hemisphere has faced Earth continuously for billions of years, and the other has faced deep space, the Moon became a divided archive. The near side tells the story of interior heat escaping through thinner crust, of lava rising and spreading into vast basaltic plains. The far side tells the story of impacts preserved, unhealed, layered one atop another like rings in ancient wood. If the Moon had rotated freely, if its orientation shifted randomly over geological time, that asymmetry would have blurred. Volcanic outpourings and impact distributions would have averaged across the globe. Instead, tidal locking froze the geometry long enough for differences to accumulate and harden into structure. The mare basalts that darken the near side formed mostly between 3 and 3.5 billion years ago, during a period when the moon's mantle still retained enough internal heat to produce widespread volcanism. Those flows filled enormous impact basins, smoothing terrain and creating the dark regions visible even without a telescope. The far side, protected by crust roughly 15 kilometers thicker on average, resisted such flooding. The result is not aesthetic contrast alone, but measurable chemical divergence. Orbital spectrometers have shown that the near side is richer in iron and titanium, elements associated with basaltic lavas, while the far side highlands are dominated by lighter, aluminum-rich anorthositic crust. That compositional difference reinforces the idea that early thermal and tidal asymmetry shaped the moon's evolution at depth. Beneath both hemispheres, however, the moon shares a common interior structure. Seismic data from Apollo-era instruments revealed that the moon has a core roughly 530 kilometers in radius, with evidence suggesting a partially molten outer layer surrounding a solid inner region. That molten portion, though small compared to Earth's core, responds subtly to gravitational forces. Tidal locking does not mean rigidity. It means synchronized motion. The entire lunar body participates in that synchronization. Slight oscillations, known as physical librations, allow scientists to probe internal density variations and confirm that mass concentrations, or mascons, lie beneath certain impact basins. These mascons alter the local gravitational field, subtly influencing spacecraft trajectories and revealing how ancient impacts reshaped interior mass distribution. Tidal locking, therefore, is not just a surface orientation but a whole-body gravitational relationship extending from crust to core. And that relationship has shaped Earth as well. Our planet's axial tilt, approximately 23.5 degrees, is stabilized in part by the moon's gravitational torque. Without this steadying influence, long-term simulations suggest Earth's tilt could drift chaotically between roughly 10 and 45 degrees. Such variation would radically transform climate cycles. At high tilt angles, polar regions could receive intense summer sunlight, melting ice caps entirely before returning to deep freeze in winter. At lower tilts, seasonal contrast would weaken, altering atmospheric circulation patterns and potentially disrupting ocean currents. The moon's presence damps these fluctuations, limiting the amplitude of Earth's axial precession. In that sense, tidal locking has indirectly contributed to climate stability over billions of years, creating a more predictable environment in which complex life could emerge. Imagine if the moon rotated independently, presenting a different face to Earth each month. The visual change might seem minor, but dynamically the system would not be in its lowest energy configuration. Gravitational torques would continue extracting rotational energy until synchronization was restored. Locking is the natural end state of tidal evolution. It represents equilibrium achieved after enormous dissipation of energy. Early in lunar history, tidal friction converted rotational energy into heat, slowing the moon's spin until its rotation period matched its 27.3-day orbital period. That equality between angular velocity and orbital velocity defines synchronous rotation. Once reached, any deviation generates restoring torque, pulling the system back into alignment. Stability is maintained not by absence of force but by continuous correction. Even the extreme cold of the far side reflects this geometry. During the long lunar night, temperatures there can plunge below -230 degrees Celsius. With no atmosphere to redistribute heat and no earthshine to provide additional reflected radiation, the far side experiences prolonged thermal isolation. Yet this isolation has scientific value. Shielded from Earth's radio interference, the far side offers one of the quietest electromagnetic environments in the inner solar system, making it a prime candidate for future low-frequency radio observatories searching for faint signals from the early universe. Tidal locking thus created not only geological contrast but also observational opportunity. The South Pole Aitken Basin, spanning roughly 2,500 kilometers and reaching depths of up to 8 kilometers, stands as a monument to the Moon's violent past preserved by stillness. Its immense size may have excavated material from deep within the mantle, exposing minerals rarely accessible elsewhere. The landing of Chang'e 4 within von Karman crater inside this basin marked humanity's first direct exploration of the far side surface. Communication required a relay satellite positioned near the Earth, Moon L2 Lagrange point, demonstrating how orbital mechanics continue to define technological pathways. Everything about this exploration, geology, temperature, communication, traces back to the simple fact of tidal locking. One hemisphere faces us, one does not, and in that fixed orientation, billions of years of history were written and preserved. Stillness, in this context, is not emptiness. It is memory maintained through gravitational balance. If you are still awake, still following the quiet logic of gravity across hemispheres and epochs, type 2 in the comments and continue listening. There is a quiet paradox at the heart of tidal locking. The Moon appears unchanged, almost frozen in place, yet that very stillness is the product of motion perfected. Billions of years ago, when the Moon spun freely, its surface experienced rapidly shifting days and nights. Earth would have risen and set across its sky in a matter of hours. Tidal forces were stronger then because the Moon orbited much closer than it does today. The gravitational pull between the two worlds generated enormous internal stress, heating the lunar interior and slowly reshaping its structure. As angular momentum transferred from spin to orbit, the Moon drifted outward while its rotation slowed. Eventually, rotation and revolution synchronized at 27.3 days. From that moment onward, the geometry became permanent. One hemisphere turned toward Earth forever. One turned away forever. That permanent orientation allowed geological differences to accumulate without averaging out. The near side experienced sustained tidal alignment with Earth, which likely influenced early heat distribution inside the Moon. Some planetary scientists suggest that radioactive elements capable of generating heat may have been concentrated slightly toward the Earth-facing hemisphere during differentiation. Combined with thinner crust, about 15 kilometers thinner on average compared to the far side, this created conditions favorable for widespread volcanic resurfacing. The mare basalts that define the near side filled immense basins, smoothing the terrain between roughly 3 and 3.5 billion years ago. On the far side, thicker crust prevented such resurfacing. When enormous impacts struck, including the formation of the South Pole Aitken Basin stretching nearly 2,500 kilometers wide and descending up to 8 kilometers deep. The resulting scars remained largely intact. Lava could not easily break through. The difference hardened into contrast. The Moon became two geological worlds sharing one gravitational fate. At an average distance of 384,400 kilometers from Earth, this relationship is both vast and intimate. Earth's gravitational field continues to shape the Moon today, generating slight tidal deformation measurable with laser ranging experiments. Even though the Moon's rotation is locked, tiny oscillations called librations reveal that its interior is not entirely rigid. Beneath the crust lies a mantle and a core approximately 530 kilometers in radius, part of which remains partially molten. That molten component responds to gravitational forces, contributing to subtle variations in rotation and orientation. The Moon's stillness is therefore dynamic equilibrium, not static immobility. It is balance maintained through continuous microadjustment. The implications for Earth are equally profound. Our planet's axial tilt of about 23.5 degrees governs seasonal cycles. The Moon's gravitational torque stabilizes that tilt, limiting chaotic variation. Without the Moon, models indicate Earth's tilt could wander between approximately 10 and 45 degrees over millions of years. Such variation would dramatically alter climate systems, reshaping ice distribution, atmospheric circulation, and ocean currents. The Moon acts as a stabilizing mass, damping extreme precessional motion. In that sense, tidal locking not only divided lunar hemispheres, but also contributed indirectly to Earth's long-term climatic stability. If the Moon were not tidally locked, if it rotated independently, the gravitational coupling between the two bodies would not rest in its minimum energy state. Over immense timescales, tidal friction would once again act to reduce rotational differences, driving the system back toward synchronization. Locking is the inevitable outcome of energy dissipation in gravitational systems. It is the configuration that wastes the least energy over time. The near side, with its broad basaltic plains, reflects a history of internal heat escaping under favorable crustal conditions. The far side, colder and more heavily cratered, preserves ancient impact history with extraordinary fidelity. During the long lunar night, far side temperatures can drop below -230 degrees Celsius. With no atmosphere to moderate extremes and no earthshine to add reflected warmth, thermal cycles are harsh and prolonged. Yet this isolation provides opportunity. Shielded from Earth's radio noise, the far side offers an unparalleled environment for low-frequency radio astronomy. The first landing there by Chang'e required a relay satellite positioned near the Earth, Moon L2 Lagrange point, demonstrating how orbital geometry defines technological solutions. Even exploration pathways trace back to tidal locking. Stillness has preserved impact basins like South Pole Aitken, where mantle-derived minerals may lie exposed. Stillness has preserved volcanic plains on the near side, their basalt frozen in time for billions of years. Stillness has preserved crustal asymmetry, revealing the early thermal and tidal imbalances that shaped the Moon's interior. On Earth, erosion and tectonics erase ancient history. On the Moon, orientation locked in space allowed history to remain visible. The contrast between hemispheres is not accidental decoration. It is gravitational biography. Every crater on the far side is a page in that biography. Every dark mare on the near side is a chapter describing interior heat and crustal weakness. The Moon's face toward Earth is familiar, almost comforting. Yet behind it lies a hidden archive shaped by the same mathematics. Tidal locking created permanence of direction, and permanence allowed divergence. Divergence preserved evidence. Evidence tells story. In this way, stillness becomes memory. If you are still awake, still listening to the quiet logic of gravity carving difference into one small world, type 2 in the comments and continue the journey. There is one more consequence of tidal locking that is easy to overlook because it unfolds so slowly: preservation through repetition. Every 27.3 days, the same sunrise sweeps across the same craters on the near side. The same long shadow stretches over the same mountain ridges. The same Earth hangs motionless in the lunar sky, never rising, never setting. On the far side, Earth never appears at all. That fixed geometry means illumination patterns repeat with mathematical precision. Over billions of years, that repetition shaped thermal stress, regolith development, and even subtle fracture propagation. When rock heats and cools in vacuum, it expands and contracts. On the Moon, where days and nights last roughly 2 Earth weeks each, temperature swings are extreme. The near side and far side experience identical solar cycles, but only one hemisphere shares its sky with Earth. Earthshine, sunlight reflected from our planet, adds a faint but measurable thermal contribution to the near side. It is small compared to direct solar radiation, yet over geological time, even small asymmetries accumulate. The far side, deprived of that reflected light, cools more deeply during lunar night, with temperatures dropping below -230 degrees Celsius. These prolonged, intense cold periods help preserve ancient surface features in a nearly pristine state. There is no atmosphere to erode, no liquid water to flow, no wind to sculpt. What changes the surface is impact, radiation, and slow micrometeorite gardening. Because tidal locking fixed orientation, the distribution of certain impact angles and exposure durations remained statistically patterned rather than randomized. The far side became a cleaner record of deep time. Consider again the South Pole Aitken Basin. At roughly 2,500 kilometers wide and up to 8 kilometers deep, it is not just a scar but a structural influence on the entire Moon. Its formation likely altered stress distribution in the crust and mantle. Being located on the far side, it remained largely untouched by the volcanic flooding that reshaped near-side basins. That preservation allowed modern missions to study exposed mantle materials, providing insight into differentiation processes that occurred shortly after the Moon formed. When Chang'e 4 touched down inside von Karman crater within this basin, it did so on terrain that had remained geologically quiet for billions of years. Communication required a relay satellite placed near the Earth, Moon L2 Lagrange point, a gravitational equilibrium region where a spacecraft can maintain line of sight with both Earth and the far side simultaneously. The very need for such a relay is a direct consequence of tidal locking. The Moon itself blocks radio signals because its orientation is fixed. Orbital mechanics dictate technology. Beneath the crust, the Moon's partially molten core, about 530 kilometers in radius, continues to respond faintly to gravitational coupling with Earth. This coupling is not dramatic. It is measured in millimeters of deformation and arcseconds of oscillation. Yet over billions of years, those minute forces shaped the Moon's mass distribution. Mascons, or mass concentrations, discovered by the Grail mission beneath major basins, reveal how ancient impacts redistributed dense material. These anomalies influence spacecraft trajectories and confirm that the Moon's gravitational field is uneven. Tidal locking allowed such asymmetries to stabilize in orientation relative to Earth, reinforcing the locked configuration. Any slight deviation generates restoring torque. The Moon does not remain aligned because forces ceased. It remains aligned because forces continuously correct. The Earth-Moon system is therefore a gravitational dialogue, not a frozen picture. That dialogue stabilizes Earth's axial tilt near 23.5 degrees. Without the Moon's steady torque, Earth's obliquity could wander chaotically between roughly 10 and 45 degrees. Climate regimes would swing dramatically. Ice sheets might grow to equatorial latitudes, then retreat entirely. Seasonal intensity would fluctuate unpredictably. Life on Earth evolved under comparatively stable obliquity, and that stability is linked to the Moon's mass and orbital configuration. Tidal locking placed the Moon in the minimum energy state required to maintain that long-term coupling. If the Moon rotated freely, gravitational torques would once again act to dissipate energy until synchronization returned. Locking is the natural endpoint of tidal evolution. It is what happens when energy has nowhere left to go. In that equilibrium, stillness preserves history. The near side preserves volcanic plains formed 3 to 3.5 billion years ago. The far side preserves dense crater fields dating back over 4 billion years. The crustal thickness difference of roughly 15 kilometers preserves early thermal imbalance. The partially molten core preserves residual heat from ancient tidal friction. The South Pole Aitken Basin preserves evidence of colossal impact energy. Even the Moon's average distance of 384,400 kilometers preserves a record of angular momentum transfer that continues today as it slowly drifts outward. All of this exists because orientation became fixed early enough for divergence to become permanent. Stillness did not erase history, protected it. The Moon is not static. It orbits, rotates, librates, drifts. But relative to Earth, its face remains constant. In that constancy, billions of years of solar system history remain visible, unblurred by rotation. Gravity, through patient dissipation, created a museum in orbit. And in that museum, the quietest surfaces hold the oldest memories. If you are still awake, still following the contrast between light and dark hemispheres, still sensing how equilibrium becomes archive, type 2 in the comments and continue listening. There is one final layer to what tidal locking created, and it is perhaps the most subtle of all. Because the moon keeps the same face toward Earth, the geometry of their gravitational coupling is permanently aligned along one axis. That alignment means the moon's longest dimension, its slight tidal elongation, points toward our planet. It is not perfectly spherical. Earth's gravity stretched it slightly billions of years ago, and when the interior cooled and solidified, that elongation froze in place. The moon is, in a measurable sense, permanently shaped by Earth's pull. Its center of mass is offset slightly toward us. Its internal density variations reflect ancient tidal heating. Its crustal asymmetry mirrors the early distribution of energy between hemispheres. Tidal locking did not simply arrange surface features. It imprinted directionality into the moon's structure itself. That directional imprint extends into orbital behavior. Even now, the moon's orbit is not a perfect circle but slightly elliptical. As it moves along that ellipse, its orbital speed changes slightly, while its rotation remains synchronized. This creates libration in longitude, allowing us to glimpse about 59% of the lunar surface over time rather than exactly half. That subtle rocking is a reminder that locking is not absolute rigidity. It is equilibrium maintained within tolerances. The moon breathes in tiny oscillations measured in degrees and arcseconds, small enough to go unnoticed without instruments, yet large enough to reveal its interior dynamics. Beneath the crust, the partially molten outer core, around 530 kilometers in radius, interacts gravitationally with the solid mantle. Seismic data suggest that this layered structure still adjusts minutely under tidal stress. These adjustments are microscopic compared to early lunar history, yet they demonstrate that the Earth-Moon system remains active. Locking is dynamic stability, not lifeless stillness. The consequences of this stability for Earth are difficult to overstate. Our axial tilt of roughly 23.5 degrees is moderated by the moon's torque. That tilt governs seasonal distribution of sunlight. If the moon did not exist, or if it were much smaller or farther away, Earth's obliquity could wander chaotically between approximately 10 and 45 degrees over long timescales. Such swings would produce extreme climatic variation. Ice sheets might advance to mid-latitudes before retreating. Tropical zones might experience freezing winters. Atmospheric circulation patterns would reorganize. Ocean currents would shift. The moon's gravitational presence damps those oscillations, keeping Earth's precessional motion within relatively narrow bounds. Tidal locking ensured that the moon occupies the minimum energy configuration required for that stabilizing effect. It is not simply that we see the same face. It is that the orientation supports long-term gravitational balance. If the moon rotated independently, the Earth-Moon system would not rest in its lowest energy state. Tidal forces would resume extracting rotational energy until synchronization reemerged. Locking is the inevitable outcome of energy dissipation in coupled gravitational systems. What makes our moon remarkable is not the mechanism itself. Many moons in the solar system are tidally locked, but the scale of its influence relative to its planet. At an average distance of 384,400 kilometers, its mass is sufficient to shape Earth's tides, influence rotation, and stabilize obliquity over billions of years. The near sides Maria, formed between 3 and 3.5 billion years ago, remain visible because nothing erases them. The far side's crater fields remain densely layered because volcanic resurfacing was limited by thicker crust, about 15 kilometers thicker on average than the near side. The South Pole Aitken Basin, spanning roughly 2,500 kilometers and plunging up to 8 kilometers deep, remains one of the most intact records of colossal impact energy in the solar system. During lunar night, far side temperatures can drop below -230 degrees Celsius, preserving surface features under extreme thermal stability. All of this crust thickness, volcanic plains, impact basins, temperature extremes exists within a framework defined by tidal locking. Stillness preserved contrast. Contrast preserved history. History preserved evidence of early solar system violence. There is something quietly poetic in that chain of cause and effect, yet it is entirely physical. Gravity stretched, friction heated, rotation slowed, orientation froze. From that frozen orientation emerged geological divergence and climatic stability. Stillness became archive. When we look at the moon and see the same familiar face, we are not seeing repetition but continuity. That face has reflected sunlight toward Earth for billions of years, while the hidden hemisphere accumulated its own silent record. One side became the storyteller of volcanic seas. The other became the archivist of impacts. Together, they represent two chapters of one gravitational equation. Tidal locking did not silence the moon. It allowed its surface to remember. And in that memory, we find not just lunar history, but clues to Earth's stability and the delicate balance that shaped our own environment. Stillness, in this sense, is preservation. It is gravity's way of holding a page open for billions of years. If you are still awake, still listening as craters and Maria settle into place across that fixed horizon, type 2 in the comments. The quiet archive of the moon remains, unchanged, waiting in the sky. Right now, as you listen, the moon is moving away from us. Not quickly, not dramatically, just 3.8 centimeters per year, about the width of 2 fingers. That number is not an estimate. It is measured directly using laser pulses reflected off mirrors left on the lunar surface by Apollo astronauts. Each pulse travels roughly 384,400 kilometers to the moon and back. The timing is precise to millimeters, and the result is clear. The distance is increasing. 3.8 centimeters per year. It sounds small, but gravity is patient. The reason for this outward drift is the same mechanism that once slowed the moon's spin into tidal lock. Tidal friction. Earth rotates faster than the moon orbits. Our planet completes one spin in about 24 hours, while the moon takes 27.3 days to orbit once. That mismatch matters. Because Earth rotates faster, the tidal bulges raised in our oceans by the moon are dragged slightly ahead of the moon's position in the sky. Those bulges contain mass, and mass exerts gravity. So the offset bulges pull the moon forward in its orbit, giving it extra angular momentum. Angular momentum cannot be created from nothing. It must come from somewhere. It comes from Earth's rotation. As a result, Earth's spin slows down. Not dramatically, about 1.7 milliseconds per century, but measurable. Ancient sedimentary records confirm that hundreds of millions of years ago, Earth's days were shorter. The moon was closer. The tides were stronger. This is not a metaphorical exchange. It is mechanical. Rotational energy from Earth is being converted into orbital energy for the moon. The total angular momentum of the Earth-Moon system remains conserved. What changes is how that motion is distributed. Earth loses spin. The moon gains distance. And this process will continue. If nothing else interfered, if the sun remained stable forever, the Earth-Moon system would slowly evolve toward a final configuration called mutual tidal locking. Right now, only one body is locked. The moon rotates once every 27.3 days, matching its orbital period. Earth does not. But in tens of billions of years, Earth's day would lengthen enough to match the moon's orbital period. Models of orbital evolution suggest that this mutual lock would occur at roughly 50 billion years from now. By that time, a single day on Earth would last about 47 of our current days. Imagine that. The sun would rise, and it would take nearly 2 months to set. The moon would no longer rise or set at all. It would hang permanently in one region of the sky, fixed above one hemisphere of Earth. On the opposite side of the planet, it would never be seen again. The tides would stop, not because gravity disappears, but because the mechanism that drives tidal friction, the offset between rotational speed and orbital speed, would vanish. With both bodies rotating in synchrony, there would be no torque, no energy transfer, no drift. The oceans would become quiet. The long conversation between Earth and Moon would fall silent. This final configuration is not accidental. It represents what physicists call a minimum energy state. For two gravitationally interacting bodies exchanging angular momentum, tidal locking is the most stable configuration available. Energy dissipates over time through friction, and the system evolves toward a state where no further dissipation occurs. Stillness is not absence of motion. It is motion resolved. We already see an example of this in the outer solar system. Pluto and its moon Charon are mutually tidally locked. Each shows only one face to the other. They orbit a common center of mass located between them. Neither rises nor sets in the other's sky. They are frozen in perfect gravitational symmetry. The Earth-Moon system is slowly moving in that same direction. But there is a complication. The sun will not remain stable for 50 billion years. In about 5 billion years, the sun will exhaust the hydrogen in its core and expand into a red giant. Its outer layers will swell outward, possibly engulfing Mercury and Venus. Earth's fate is uncertain. Some models suggest our planet may be swallowed. Others suggest it may survive in a widened orbit as the sun loses mass. If Earth survives, the Earth-Moon system will not be unchanged. As the sun loses mass through stellar winds, Earth's orbit will expand. The moon's orbit will expand with it. Solar tides, currently negligible compared to lunar tides, may begin to dominate. Gravitational perturbations could alter the Earth moon balance long before mutual tidal locking is achieved. So in reality, the theoretical 50 billion year endpoint will almost certainly never be reached in its pure form. The sun will intervene, but the direction of evolution is still clear. The moon is not falling toward Earth. It is moving away. Could it escape entirely? To escape Earth's gravity, the moon would need to reach escape velocity relative to Earth, about 5,800 kilometers per hour. Tidal drift does not provide that much energy. As the moon moves farther away, tidal forces weaken dramatically, decreasing with the cube of distance. The outward push slows over time. The moon will not crash into Earth. It will not spiral inward. It will not be flung away violently. Its path is gentle. Gravity is not dramatic. It is persistent. And what persistence produces over billions of years is balance. In the next part of this journey, we will look more closely at what that final balanced state would feel like, what it would mean for climate, for oceans, for the sky itself, and why the moon's apparent stillness is not a coincidence, but the inevitable conclusion of energy-seeking equilibrium. If you are still here with me, still traveling forward through billions of years of orbital mechanics, simply continue. If mutual tidal locking were allowed to complete its slow progression, the Earth-Moon system would become something profoundly different from what we experience tonight. At that distant equilibrium, Earth would rotate once every roughly 47 current days, matching the Moon's orbital period at its expanded distance. The Moon would remain fixed above one hemisphere, never rising, never setting. For half the planet, it would be an eternal presence in the sky. For the other half, it would never appear again. The familiar rhythm of waxing and waning would disappear, because the lunar phase cycle as we know it depends on the interplay between Earth's rotation and the Moon's orbit. In the mutual lock state, the geometry becomes static. There would still be phases in the physical sense of illumination by the sun, but from any fixed location on Earth, the Moon's position in the sky would no longer change. The sky itself would feel slower, heavier, stretched across weeks instead of days. The tides, which today are powered by the misalignment between Earth's faster rotation and the Moon's orbital motion, would largely cease. There would still be solar tides, but they are significantly weaker than lunar tides. The great twice-daily breathing of the oceans would quiet. Coastal ecosystems shaped by tidal rhythms would no longer exist in the same way. The dissipation of tidal energy, currently about 3.7 terawatts, would approach zero because there would be no torque-driving energy transfer. The system would have reached its minimum energy configuration, the state toward which it has been evolving for 4.5 billion years. To understand why this configuration represents a minimum energy state, we return to angular momentum conservation. The total angular momentum of the Earth-Moon system is the sum of Earth's rotational momentum and the Moon's orbital momentum. Tidal friction redistributes this momentum but does not destroy it. As Earth slows, the Moon moves outward. The outward motion increases the Moon's orbital angular momentum while decreasing Earth's spin angular momentum. Eventually, when the rotational period of Earth matches the Moon's orbital period, there is no longer an offset tidal bulge. Without an offset, there is no torque. Without torque, there is no further transfer of angular momentum. The exchange ends naturally. Physics does not seek drama. It seeks stability. Mutual locking is not an exotic outcome. It is the mathematically inevitable endpoint of dissipative gravitational systems given enough time. We already see a completed version of this configuration in the Pluto-Charon system. Pluto and Charon are mutually tidally locked, each showing only one face to the other. Their barycenter lies outside Pluto's surface, meaning they orbit a common point in space rather than one clearly dominating the other. The Earth-Moon system does not currently behave this way because Earth's mass is much greater than the Moon's, and the barycenter lies within Earth's interior. But in terms of rotational synchronization, the future mutual lock would resemble Pluto and Charon's frozen partnership. It would be a stable binary dance, slowed to perfect symmetry. However, unlike Pluto and Charon, Earth and Moon exist in the gravitational field of a much larger star whose own evolution will intervene long before 50 billion years pass. The Sun's red giant phase, expected in about 5 billion years, changes the context entirely. As the Sun exhausts hydrogen in its core, it will expand dramatically. During this phase, the Sun will lose a significant fraction of its mass through stellar winds. When a star loses mass, the gravitational grip it exerts weakens. Planetary orbits respond by expanding outward. Earth's orbit would widen. The Moon's orbit around Earth would adjust accordingly. The tidal interaction between Earth and Moon would continue, but the changing gravitational environment could destabilize the delicate long-term evolution predicted under a stable Sunday. Some models suggest Earth may be engulfed. Others suggest it may survive in a more distant orbit around a dim white dwarf remnant. In either case, the theoretical 50 billion year mutual lock will likely never be realized exactly as calculated under present conditions. Stellar evolution sets a deadline shorter than tidal evolution. Importantly, none of this implies catastrophic collision or escape. The Moon is not spiraling inward. The direction of energy transfer is outward. To escape Earth's gravity, the Moon would need to achieve escape velocity relative to Earth, approximately 5,800 kilometers per hour. Tidal drift cannot supply that magnitude of energy. As distance increases, tidal forces weaken rapidly, scaling with the inverse cube of separation. The farther the Moon moves, the weaker the torque becomes. The drift slows naturally. Escape through tidal evolution alone is effectively impossible. Likewise, inward collapse is not supported by the current angular momentum distribution. The system is stable, and stability increases as it approaches synchronization. What remains most remarkable is that this entire future trajectory is not speculative fantasy but the direct extrapolation of present measurements. The 3.8 centimeters per year recession rate, the 1.7 millisecond per century lengthening of Earth's day, the conservation equations governing rotational dynamics, all point in the same direction. The Moon's stillness is not a static feature. It is the visible result of an ongoing process of energy redistribution. Every tide that rolls onto a shoreline participates in this transfer. Every fraction of a millisecond added to Earth's day is part of the same story. Gravity continues its quiet negotiation, centimeter by centimeter, millisecond by millisecond. In the final part of this journey, we will step back from the equations and look at the philosophical conclusion that physics quietly suggests. That the moon's stillness is not an accident, not a frozen relic, but the natural end state of motion-seeking balance. And when you look up tonight and see that familiar face, you will know you are witnessing not permanence, but a system slowly, patiently, mathematically moving toward rest. If you have made it this far through billions of years of orbital evolution, stay with me for the final stretch. When we step back far enough, beyond centuries, beyond civilizations, beyond even the lifespan of the sun, the story of the moon becomes something deeply simple. Energy moves, friction dissipates, motion redistributes itself until no further exchange is possible. What we call stillness is not the absence of motion, but the end state of motion resolved into balance. The moon's locked face is not frozen by force. It is settled by mathematics. Right now, the Earth-Moon system is still evolving. The moon recedes at 3.8 centimeters per year. Earth's day lengthens by about 1.7 milliseconds per century. These numbers seem trivial because human life is short, but orbital mechanics does not measure in decades. It measures in millions and billions of years. Over 100 million years, the moon moves nearly 3,800 kilometers farther away. Over 1 billion years, Earth's day grows noticeably longer. This is not hypothetical. Fossil tidal rhythmites in ancient rock layers show that 400 million years ago, Earth experienced roughly 420 days per year. The planet rotated faster. The moon was closer. The tides were stronger. The system has already changed dramatically. It will continue to do so. If we imagine the far future equilibrium, Earth rotating once every 47 current days, the moon fixed permanently above one hemisphere, the visual consequences would be profound. On one side of Earth, the moon would never set. It would hang in the sky like an unmoving sculpture. Clouds would pass in front of it. Seasons would shift beneath it. Continents would drift. But the moon would remain fixed in place. On the opposite hemisphere, generations would live and die without ever seeing it. The cultural meaning of the moon, our ancient calendar, our poetic symbol of change, would disappear. There would be no waxing or waning in the sky from a given location. No monthly cycle to mark time. The night would lose one of its clocks. The oceans would feel the difference most. Today, tidal friction dissipates about 3.7 terawatts of energy in Earth's oceans. That energy becomes heat and orbital momentum. In a mutual lock state with no offset between rotation and orbit, that dissipation would effectively cease. Tides would not vanish entirely, solar tides would remain, but they would be weaker and far less dynamic. The powerful mixing of ocean layers driven by tidal forces would slow. Climate patterns, which depend in part on ocean circulation, would evolve differently. The Earth of that era would not resemble ours in geography or biology. But the physics would be clear. Without differential rotation, there is no tidal torque. Without torque, there is no energy exchange. The principle governing this evolution is conservation of angular momentum. It is one of the deepest laws in physics. In a closed system, angular momentum remains constant. What changes is its distribution. Early in the moon's history, it rotated rapidly. Tidal forces slowed that rotation and transferred angular momentum outward into its orbit. Now Earth's rotation continues to feed the moon's outward drift. Eventually, when both bodies share the same rotational period, the redistribution ends. The system reaches its minimum energy configuration for the given total angular momentum. This is not a preference. It is not a goal. It is the inevitable mathematical endpoint of dissipative gravitational coupling. It is important to emphasize what will not happen. The moon will not crash into Earth. The direction of tidal evolution is outward, not inward, nor will it likely escape entirely. To escape, it would need to reach approximately 5,800 kilometers per hour relative to Earth. Tidal forces cannot supply that much energy, especially as the interaction weakens with distance. As separation increases, the gravitational torque drops rapidly. The recession slows. The system asymptotically approaches stability. Escape through this mechanism is extraordinarily unlikely. The future is not catastrophic. It is gradual. But long before 50 billion years pass, the Sun will intervene. In about 5 billion years, it will enter its red giant phase. Its radius will expand enormously. Its luminosity will increase. Earth's oceans may boil. The atmosphere may be stripped. The Sun will lose mass, and planetary orbits will expand. Whether Earth survives intact is uncertain. The Moon's fate depends on that survival. If the Earth-Moon pair remains gravitationally bound after solar mass loss, their mutual tidal evolution could continue around a white dwarf Sunday. If not, the system may be disrupted. Stellar evolution is faster than tidal evolution. The red giant clock runs out before the mutual lock clock finishes. And yet, even knowing that, the direction of the system remains meaningful. It tells us something fundamental about the universe. Systems with friction evolve toward equilibrium. Energy gradients flatten. Motion dampens. Extremes soften. The Moon's stillness is not an anomaly. It is a preview of how gravitational systems age. There is a quiet beauty in that. The same physics that shaped galaxies and stabilized planetary systems operates here, between Earth and its companion. Billions of years ago, a violent collision with a Mars-sized body created a molten debris disk. From that chaos emerged a moon spinning rapidly in the sky. Gravity stretched it. Friction slowed it. Angular momentum redistributed itself. The moon locked. Earth began to slow. The drift outward continues. The future is not random. It is a continuation of the same equations. When you look up tonight and see the same familiar face, you are not seeing a static object. You are seeing a system mid-process. The stillness is temporary in human terms, but inevitable in physical terms. The moon's fixed gaze is the visible expression of energy having found balance. It is not mystical. It is measurable. One day, far beyond human history, the tides will quiet, the days will stretch, and the sky will change. The Earth-Moon pair will either approach perfect symmetry or be reshaped by the aging sun. But the underlying truth remains. The moon's stillness is not a mystery. It is the natural end state of motion-seeking equilibrium. If you have traveled all the way from violent impact to distant mutual lock tonight, through billions of years of drift and balance, simply type 3 in the comments. It's a small signal across a small distance compared to cosmic scales. But like the laser pulses we send to the moon, it confirms that the connection is still there. There is something quietly humbling about knowing that the moon is not permanent in the way we instinctively feel it is. For all of human history, it has kept the same face toward us. Empires rose and fell beneath that steady gaze. Oceans moved in their tidal rhythm. Calendars were built around its phases. Myths, religions, navigation, agriculture, all synchronized to that predictable cycle. And yet, beneath that appearance of permanence, the system has never stopped evolving. The 3.8 centimeters per year outward drift may seem insignificant, but it is relentless. Every year, the moon moves just a little farther away. Every century, Earth's day lengthens just a little more. These changes accumulate silently, invisibly, beyond the scale of human awareness. If we compress millions of years into seconds, the moon would appear to glide outward like a slow exhale. The Earth would rotate more sluggishly, its spin gradually surrendering energy to the orbiting companion. This exchange is not destructive. It is not chaotic. It is a redistribution toward stability. Angular momentum is conserved. Energy dissipates as heat in the oceans. The system moves toward its lowest energy configuration, because that is what systems governed by friction always do. They settle, they quiet, they resolve tension. The concept of a minimum energy configuration is central here. In physics, systems naturally evolve toward states that minimize free energy under constraints. The constraint for Earth and Moon is total angular momentum. Within that constraint, tidal friction slowly removes mechanical energy while preserving the overall momentum budget. The result is increasing orbital distance and decreasing rotational speed. When both bodies rotate with the same period, no further energy can be dissipated through tidal torque. The bulges align. The torque vanishes. The exchange ends. This is not poetic. It is mechanical inevitability. We can observe the same principle in smaller ways. A spinning top eventually wobbles and settles. A pendulum loses amplitude and comes to rest. A rotating binary star system exchanges mass and angular momentum until it stabilizes. The Earth-Moon pair is simply a larger expression of that same rule. The difference is scale. Instead of seconds or minutes, the settling process takes billions of years. Instead of friction in air, it is friction in oceans and planetary interiors. But the mathematics is the same, and so the moon will not crash into Earth. It will not suddenly fly away into interplanetary space. Its escape velocity relative to Earth is about 5,800 kilometers per hour. Tidal forces do not provide that magnitude of acceleration. As distance increases, gravitational interaction weakens dramatically. The outward drift slows naturally. The path forward is gradual asymptotic approach toward equilibrium, not dramatic rupture. The only major interruption comes from stellar evolution. In about 5 billion years, the Sun's transformation into a red giant will reshape the entire inner solar system. If Earth survives that expansion, stripped and altered but still gravitationally bound to the remnant star, the Moon may continue orbiting it in a changed environment. If Earth does not survive, the Earth-Moon story ends differently. But up until that stellar deadline, the trajectory remains clear. Slow drift, slowing spin, quiet redistribution. It is worth pausing to consider how extraordinary it is that we can measure and predict this future. Laser ranging experiments bounce photons off reflectors placed on the Moon more than half a century ago. Those photons take about 2.5 seconds to make the round trip. From their timing, we detect millimeter changes in distance. From those millimeters, we calculate centimeter per year recession. From those centimeters, we extrapolate billions of years of evolution. The chain from photon to future is unbroken. The Moon's stillness, then, is not a static condition. It is a stage in an unfolding process. When we say the Moon never turns, we are describing a temporary equilibrium within a larger evolution. It already turned once, rapidly in its infancy, is slowed, is synchronized. Now Earth is slowly following. In the deep future, both may share that same lock. And even that state would not be eternal. Nothing in astrophysics truly is. Perhaps the most beautiful conclusion is this. The Moon's fixed face is not an accident, not a rare cosmic coincidence, but the predictable outcome of gravity and time. Given enough mass, enough friction, and enough billions of years, motion smooths itself into balance. Chaos cools into rhythm. Spin aligns with orbit. The system quiets. When you look at the Moon tonight, you are seeing a snapshot of energy halfway through its long descent toward equilibrium. The tides you hear on distant shores are part of that descent. The slight slowing of Earth's spin is part of that descent. The centimeter drift outward is part of that descent. It is all one continuous equation unfolding across time. And one day, long after human memory, long after continents shift and climates change, the Earth-Moon system will either approach mutual stillness or be reshaped by the aging sun. Either way, the direction is governed not by myth or chance, but by conservation laws written into the fabric of the universe. The Moon's stillness is not frozen. It is resolved. It is what happens when motion has negotiated with gravity for billions of years and found the quietest possible arrangement. If you have stayed through this entire journey, from violent formation to tidal locking to distant equilibrium, then you have followed the full arc of gravitational time. If you made it all the way here tonight, gently type 3. It is a small gesture across a small distance, but like every gravitational exchange, even small signals connect worlds.